Let me wait for 1 more minute. All right. So good morning, everyone. Uh, so let's get started, students. So wish all of you a very happy Krishna Janmashtami, and hopefully, all of us have a nice day today. We must find some time to enjoy the festival as well. So though we are the campus, we are working today. Other campuses have holiday for Krishna Janmashtami, but doesn't matter. That's the Krishna's message, right? That we must be doing our task, right? Always. So we need to follow what we are supposed to do. So fine. So with that, okay. So let's get started. So we have 3 weeks, 3 days, 3 classes this week before we start with our mid-semester exam. So 3 lectures. I think we must be able to do these 3 lectures. Uh, Graphs, L7 is graphs, that we may be able to do it today. And then MST is the next lecture is shortest path, and then it is MST. So probably we can finish L7 and L8. I will try to finish L7 and L8 in these 3 days, in these 3 classes. All right. So it's all, it's kind of revision only for you. Maybe few terms you will see that it is new. Okay. So what is a graph, right? So we will define a graph as, definitely this picture represents a graph, but what is a graph? We define a graph as a graph is a set of vertices V. V is a set of vertices V, and a set of edges UV belongs to E. That is, when I say a set of edges, UV must belong to E. There are set of edges where U and V belongs to V. So the edges are made up of vertices, right? So AB is an edge, AD is an edge, EF is an edge. So whichever edge I have, the vertices of the edge must belong to V, right? So how do graph differ? And you can define various, the graphs can be described various ways, they can be classified various ways, all that is there. Yes, how do graphs differ? What are graph characteristics we might care about, right? So first we will talk about undirected graphs. Undirected graphs are graphs wherein edges do not have a direction, right? So the example we are seeing so far, it is here, this is an undirected graph. There is no direction in the edge. So you can also call it as bidirectional. So you will say that AB is an edge, and so BA. AB is there and there is a connection from B to A. No restriction while moving from A to B or B to A. Then we talk about directed graphs. So in directed graph, edges do have a direction. So this is an edge. BA is an edge, but there is no edge called as AB. There is no direction from A to B, but the direction is there from B to A. So this is a directed graph. Edges do have a direction, right? Another classification is weighted graphs, wherein edges have an associated weight that we are seeing. So before that, in this example, you can say that the previous example, this example, it does not have a weight. It's a directed graph without weight. So now this is a, you can say, undirected graph which has a weight, right? Now this is a graph which is a directed graph as well as it's a weighted directed graph. it has weights, edges have weights as well, right? Then we will talk about the terminology, the definition. What is a path? Right? So a path is a list of vertices P1, P2, Pk. We go from P1 to Pk, where there exists an edge. For every Pi to Pi plus 1, there must be an edge. So if I am saying P1 to Pk is a path, so P1, P2, P2, P3, P3, P4, like that, we should have a path. We should have an edges. So that becomes my path, right? So for example, I can say that this set represents a path A, B, D, E, F. How I am saying? Because A to B, I have an edge. B to D, I have an edge. D to E, we have an edge. And E to F, we have an edge. So it's a path. A, B, D, E, and F. Red color is a path. Right? Then, a path is a list of vertices, right? Where we are seeing this. Now, if you say CD, is it a path? Yes. CD also is a path here. Because you have an edge. Though this path has only one edge possible. But this is a path, right? This is the condition that Pi plus 1, it can be anything like P1, P2, but there should be a direct edge. What do we mean by a simple path? Generally, when we say path, by default, we always mean a simple path. If it is not mentioned, it is a simple or some other path, by default, we take it as a simple path. So a simple path contains no repeated vertices. Often this is implied. Okay, so in a simple path, we do not consider a repeated vertices. Vertex cannot be repeated in a simple path. All right. And then what is a cycle? A subset of the edges that form a path such that the first and the last node are the same. Right? We defined path. When we defined path, we said that simple path does not have a repeated vertex. Okay, there should not be no vertices that is repeated. When we define cycle, we say that cycle is a subset of edges. Okay, so it may be, subset, or we are not saying a proper subset of edges, that is some edges that form a path. It's a path such that the first and the last node are same. Right? For example, here in this picture, A, B, D is, we can call it as a cycle. Now you may be thinking that, why I have not repeated A, because I am representing it in a form of a set. But what I am trying to say here is AB, BD and DA. Okay, AB, BD and DA, that is a cycle. Because while I am traveling to this path, okay, it's a subset of edges. When I am considering these edges, the first and last vertex are the same. So this becomes a cycle. What about AB? It is not a cycle. It's an edge. AB is an edge. It is a path. But when you mention this edge, it's only one edge, where the first and the last node are not same. So this is not a cycle. Now let's say this is a path given. This is a graph given. Okay. Now the question is this a cycle? A, B, D, is it a cycle? Let us check. A, B, D. The set is given as ABD. So what are the edges? I have edges as BA. I have edges as BD. I have edge as DA. So let's say if I start from B, I have BD, I have DA, but there is no AB, right? So this is not a cycle because it's a directed graph and there is no edge, that if you just consider, you need to consider the edges, and by considering edges, we are not getting a cycle. So this is not a cycle. Very small difference. We simply by seeing a loop, we cannot say that it is a cycle. We must see that whether there is an edge that is making it a cycle or not. It is not making it a cycle. Now here, so what exactly is the definition of a cycle here? That as shown in the picture, it's, for example, here it's a path P1, P2, Pk, wherein we see if P1 is the first node, or you can say first vertex, and Pk is the last vertex, then P1 is equal to Pk. Right? So the same example, we have just changed the edge direction. So this makes a cycle. A to B, B to D and D to A. We have three edges here, and when you see these three edges together, you get a cycle. Right? So that's the definition of, that's the basic terminology. But whenever we deal with a graph, we need to understand, we need to keep in mind what kind of graph it is, right? Now, what is the meaning of a connected graph? Okay, so connected means you say that a graph is connected when every pair of vertices is connected by a path. That means I am able to reach from a vertex to any other vertex. Then it's a connected graph. You must be thinking that, we always deal with connected graphs. So in most of the problems that we deal in computer science, we have the graph that is connected. You are able to reach from one node to every other node. Right? But after learning your networking course, you know that, some part of the network can be disconnected for some time, because if the nodes are connected in between via other nodes, one node may go down. So the graph can be disconnected as well. Right? So the meaning of connection is every pair is connected by a path. Okay. So this example looks like that everything is connected. Yes, it is connected, right? Because you can reach, if I want to reach from A to G, I am able to reach. There is a path that exists. Okay. Now let us see this example. So now we just said connected first. Now we are saying connected, and then we are talking about undirected graphs. This graph does not have a direction. And if you see, there is no edge here. So I can call this as a not connected graph. Okay, just an example. These are just examples. So in this example, because I do not have an edge, this is an undirected graph, and I can say that it is not connected, because if I want to go from A to G or A to E or D to F, I am not able to go. So it is not a connected graph. Now, the next terminology, okay, is called as strongly connected. Okay, strongly connected. So strongly connected terminology we use with directed graphs. Okay, one is connected. See, connected terminology we use with undirected graphs. Okay, connected terminology we use with undirected graphs. We saw the examples. This was a connected graph. This was an undirected graph which was connected. This was an undirected graph which was not connected. Now we are talking about strongly connected graph. Okay, so strongly connected term is used with directed graphs. Okay, so connected we use with undirected graphs. When we use the term strongly connected, we use this term strongly connected with directed graphs. The definition is same, that every two vertices are reachable by a path. Then you say that it's a strongly connected graph. First of all, it's a directed graph. When do I say the graph is strongly connected? I will apply whether a graph is strongly connected or not only with directed graphs. Once I see a directed graph and I am able to find that any two vertices are reachable by a path, then we say that it's strongly connected. So is this graph strongly connected?
No, ma'am.
No. Certainly no, because there can be many cases. If I want to reach from F to E, I cannot. F to A, I cannot reach, right? Because of the direction in the edge. So this is not a strongly connected graph, right? Now we have made the graph change like this. Okay, we are trying to see whether this is now strongly connected or not. I am able to reach from F to A, but still I am not able to reach from G to E, right? So this is also not strongly connected graph. Now we will see. Now we have the same graph, we have just changed it. It looks like it is strongly connected. Let us just verify. I can reach from A to B, A to E also, A, B, D, E. A to F also, A to G also, B, yeah, F. I think this is a strongly connected graph. We are able to reach from every vertex to every other node. From E to A, I can reach. From E to D, I can reach this way. I mean, there is a path. A path should be existing. A to G, G to F, F to A, I'm able to reach. This is a strongly connected graph, because I'm able to reach from every two vertices are reachable by a path. Reachable by a path. Okay.
Ma'am,
Yeah.
can we say that if there exists a cycle within the directed graph, it'll be reachable. Every node will be reachable.
What are you saying? Please say again.
Ma'am, if there exists a cycle within the directed graph,
Then you are able to reach. That's what you want to make a hypothesis, is it?
yes, like, uh, can I say it that way or?
Uh, see, if we say that hypothesis, we must be able to prove it in all cases. Maybe in this example you are able to see. Maybe in this example it is
Like
doable
if
because. Huh?
actually if we remove the edge from F to A, then it is not strongly connected.
Yes. Yes.
But there exists a cycle, no, ma'am. There exists
No.
like
I understood your point. See, what you are saying is, no, there is one cycle, A, B, D, A. There
no,
is
I'm not
another
talking
cycle.
about a small cycle. I'm talking about a cycle in which all the nodes are involved, like the one that's there here.
Understood. Then it is, yeah. You are saying that you have a directed graph wherein there is a cycle, right? Yeah,
Yes.
then, yeah, you can consider any design, any hexagon, octagon, right? A, B, C, D. So, yeah, and if it's a directed graph and if there is a cycle means definitely, yeah. Then it's a strongly connected graph. So for
Okay.
example, when you said this, wherein a cycle wherein all the nodes are involved, that just brought a picture of, let's say, octagon to my mind. Everything is connected and it's directed in a way that it is forming a cycle. Then yes, you are able to reach from every node to every other node. Yes. But if I make a hypothesis that there is a cycle, if there is a cycle, any cycle, there is only one cycle here, right? No, two cycles are there. One is this, one is this, and this, right? So is it possible then? It may be or may not be. I am not sure. We have to prove it by that every case it will happen or not. Okay. So fine, good. So then we talk about tree. What is a tree? Okay. So in our terminology, if I say, is this a tree? All of you will say, yes, it is a tree. Right? So true. Fine. This is a tree. Okay. So what exactly, if I want to define a tree, then tree is a connected. It has to be a connected. That's why we learned why we are talking about connected graph. First of all, it's undirected graph. So we are not talking about something called as strongly connected, but definitely if it's an undirected graph, we don't have to worry whether we are A to B is there. By default means B to A, we are connected, right? So it's an undirected graph, tree. When we define tree, we say that it's an undirected graph and it's a connected graph. Connected graph means, it is not that some part of tree is lying somewhere else. It's all connected and there should not be any cycle. That is how we define a tree. Simple definition. Definitely, if you have to consider a definition of tree mathematically, you will say set of vertices, set of edges, all that you will define. But if we consider that we have all those terms defined already, we will say that tree is a connected, undirected graph without any cycle. Now, one thing is missing in this picture, in this diagram. Okay, so it looks like a tree, nice. Okay, and we all consider it a tree. But the one thing that is missing here, that is an important part. When I say it's a tree, can anybody tell? Fine, this is a tree, but one important part is missing here. That must be mentioned. What is
Root
that?
of
Root of the tree. Yes. So if a tree is given to me, they should also tell, right? We must say that what is a tree. When if it's a tree, nobody is telling me. It's not necessary that this first thing that will come to my mind is, yeah, B is the root. But who is telling B is the root? I can make A also as a root, F also as a root, E also I can make a root, and then I can draw my tree, right? I can make D as a root and then make all this as going left, right, like that, right? So the another important part is, whenever a tree is defined, tree must have a root, right? There has to be a single root in the tree. So that is missing in this definition. That should also be there. So that is important, right? So for example, this is the tree, and now let me say this is my tree, and no, this is just a picture to say that this C can be drawn like this also, right? So far in this previous picture, I will say that C is my, B is my root. They have not told me what is the root. Let me take B as a root. What if the picture is changed like this? Then should I consider C as root? So that is why we need to specify a root. Okay. The same picture can be drawn like this also. A to F. See, A to F, C to B. I can also draw it like this. So now what should I do? Should I consider A as root? So that is why root is an important part that has to be there. When I say this is my tree, I must also say that what is the root of the tree, right? So fine, that all of you know all those things. Then we talk about another graph which we will be using. Okay, DAG, that is called as directed acyclic graph. We will be using it for some scheduling techniques. We will be using it. Okay, so directed acyclic graph, as the name indicates, it's a directed graph that must not have a cycle, right? It's a directed graph that is not having a cycle. So here, though it looks like a cycle, it's not a cycle. Acyclic, there is no cycle. So yeah, so there is no cycle in this. Just an example. We will be talking about this. What for DAGs are used. What is the use of DAG? You know, how we use them in scheduling or for performing some specific kind of sorting techniques. A topological sort, when we use that time, we can use DAG, directed acyclic graphs. That is where they are used. We will be discussing that after midterm exam. Okay. Then different type of graphs are complete graph. Another kind of graph. That complete graph means there is a connection, an edge between every two nodes. An edge exists between every node. It's a complete graph. A to B, A to C, A to F, A to D, like that. And if it's a directed graph, then definitely everywhere you will find two edges. A to B also, B to A also. Then you will call it as a complete graph. Okay. Then this is another nice important definition, bipartite graph. This will be used, those bipartite graph. Uh, it is used in the problems, where you have some set of, again, I will say in larger terms, I can say it is used in scheduling techniques, again, bipartite graph. Okay, I can give a quick example. Suppose you are making a timetable, there you have, let us say, 10 teachers, and you have some 20 classes or 10 classes, 10 teachers or 15 classes, let us say. You want to assign each teacher to a class, right? And it should be something like this. You have minimum 10 number of classes that you need to assign, and then there will be conditions that a teacher can be assigned only to class 1, 2, 3, and another teacher can be assigned only to class 2, 3, 4. Like those conditions can be there. Okay, so these kind of problems, so what are the kind of problems? The kind of problems are, you have two sets. Okay, you have two sets, and what you want to do is you want to connect one set with another set, and there is a condition that has to be satisfied for making a connection. Okay, so there will be an edge. A teacher will be assigned to a class, and such that every teacher must be assigned to at least one of the class. Something like that. The conditions may be there. Okay, so there we do, for solving such problems, we actually convert it to bipartite graph. So what is the definition of bipartite graph? Bipartite graph is a graph where every vertex can be partitioned into two sets, x and y, such that all edges connect a vertex u belongs to x and a vertex v belongs to y. Okay, so first of all, when you bring a vertex, you should be making that vertex into set x or set y. Either it can be a teacher or it can be a class. Okay, so teacher is a person and class is, let us say, class 1, class 2, class 3, like that. Okay, so a vertex, we cannot fall into both the classes. A vertex has to fall only into one class. Every vertex can be partitioned into two sets. Either it will go to set x and set y, and there has to be an edge. So whenever you have an edge, okay, The edge should be such that one vertex of that edge belong to one set, another vertex of that edge belong to another set. What do I mean by saying that? The meaning is a teacher will not be connected with itself. Okay, or a classroom will not be connected with itself, because you want to assign a teacher to a classroom, right? So classrooms themselves are not connected and teachers themselves are not connected. So whenever there is a connection between a teacher and a classroom. That is the meaning. So such kind of problems are there in computer science. Those are solved with bipartite graphs. So these are kind of, you can say, special data structures. Those are used for solving a specific kind of problems. Okay. So this teacher and classroom is one example. It can be many things, in operating system, you can apply some set of services to some set of classes. Like that, you can have various ways of scheduling something. Okay. So when do we see graphs in real life problems? Everywhere, right? Everywhere you see graphs, right? So network can be a common term. Wherever you can draw a network, there you can apply the graphs. So transportation networks, flights, roads, you have pipelining, water line, your many electric lines, many things are there. Then you have communication networks, you have web, you have social networks, circuit designing, various kind of networks, Bayesian networks. Wherever you see a network, a connection, basically you can apply you can apply the graph data structure to solve various problems. Okay, why do I want to apply? Because ultimately I want to solve a problem. For example, I have a pipeline wherein the water is coming from some, there is a specific flow and there are various taps, a full pipeline, water pipeline, and I want to control the flow such that every line should get a minimum flow. Every line should get a minimum flow, and if I have enough water, few lines may be given higher flow if it is available, like that, right? In transportation networks also, we would have seen, we have many flights. You want to go to Bangalore to let us say Hyderabad, for example. So there may be various routes. One will be direct flight Bangalore to Hyderabad. Maybe one first goes to Delhi and then from Delhi to Hyderabad. Now, depending on how much time it takes, what is the cost, so many problems we want to solve, right? Accordingly, we choose we choose the flight. Sometimes I want to go to Hyderabad, but if I go via Delhi, probably that is taking less cost. Sometimes, due to some economic reasons or some seats are free or something, so I may take that path also, right? So rather the flight I was spending 1 hour, maybe I am ready to spend 1.5 hours because it is costing me less, right? So what I'm trying to say is, wherever there is a network, we can make a graph and we can apply various algorithms. Apply algorithm means, now I am making a graph for finding out what do I want to find the shortest path. I want to find out minimum cost in terms of rupees. I want to find out minimum cost in terms of time, right? Or I have a full day to spend, I don't have any other task. I just want to spend my time in roaming around. Probably I want to just be in flight. Okay, so I want to take a maximum path. That can also be a problem that I want to solve. What is the maximum path that is going to take, right? So all those, so wherever we want to find out these kind of uh, you know uh, these kind of solutions, maximum path, minimum path, maximum throughput, all those things, my idea, maybe I want to cover more number of hops. Somebody may be crazy, I want to go to Chennai, but in between I want to cover maximum number of hops. So I want to take a flight from here to there, then finally I want to reach Chennai. Probably I want to make a record that I took so many hops. Anything possible, no? So accordingly, we will formulate what graph suits me and what exactly we want to do after making the graph, right? So That's what. So now the next fundamental problem is, yes, I can solve any problem. I have to transfer my problem into a graph. And now how do I represent my graph? All of you know that there are two ways. One you call as adjacency list, another one you call as adjacency matrix, right? So in adjacency list, so the definition is you have a given graph and you have various vertex. So for every vertex, okay, every vertex there is an adjacency list. Okay, so we define it that each vertex u belongs to V contains an adjacency list of the set of vertices V such that there exists an edge UV belongs to E. Okay, what does it mean? You take a vertex U, for example, A. Okay, so you are going to make a adjacency list. How will you make adjacency list? Now you will find out all the edges that starts with A. For all the edges UV, you are going to add that vertex V into adjacency list. For example, for A is connected with B and D, directly connected with B and D. It is not that A is connected. Yes, A is connected with everything here. If it's an undirected graph, right? But I will only see the nearest connection, or you can say one hop connection. So A is connected with B and D. So there is an edge AB. So B will get an entry in the adjacency list of A. Similarly, D will get an entry in the adjacency list of A. So each vertex U belongs to V contains an adjacency list, that is what we call as adjacency list, of the set of vertices V such that there exists an edge UV belongs to E. So now if I get it like this. For A it is BD, for B is connected with A and D. For C is connected with D directly, only with D. D is connected with all four, A, B, C and E is connected with D. Okay, so the important thing is each vertex is going to have an adjacency list such that if I am saying that for D there is A, B, C, D, that means I should have an edge DA, I should have an edge DB, I should have an edge DC, and I should have an edge DE. That is the meaning. That is with adjacency list. So the next thing is so now what we did is we changed the graph. This was an undirected graph. Now this is a directed graph. In this directed graph, just to make it more clear, now from A I will have only B, right? Because only A is connected only with B. There is no edge that starts from A. Why we took this example is to tell we are seeing when we are dealing with vertex U, all the edges that starts with U that we need to cover. So when now in this graph A to B will come, but D to A will not come. See, when you see A, so I am searching each vertex U such that the edge UV belongs to E. What is the meaning of UV belongs to E? The edge has to start from U. So AB will come, but DA will not come in A. Okay. In B, there is nothing. Nothing is starting from B. So that's why definitions are important, students. When we say definition, so this definition we must keep in mind. Set of vertices V such that there exists an edge UV. That edge is starting from, it is not VU, it is an edge. That's why we are so specific that for vertex U, we are looking for edges UV, not VU. Okay, UV is different, VU is different. So we are looking for edge UV. So for B, it is nothing. For C, it is CD. For D now, earlier it was 4. Now it is DA, DB. That's it. So DA and B we have covered. And for E, it is D. Fine. Then we talk about adjacency matrix. So again, we will take both the examples. In adjacency matrix, A, V cross V matrix, right? A, B, C, D, E, you have 5 vertex. So it's a 5 cross 5 matrix such that Aij, that is the value of Aij is equal to 1 if there is an edge. Ij is an edge, otherwise it is 0. Right? So that's about the adjacency matrix. So A, B, C, D, E. Now if you want to make, so A with itself it is going to be 0 because you will not consider that as an edge. There is no edge. You are in the same node. A to B, D, A to B, D, like that. B to AD, same thing. It's the same picture. From D, if you make 1, 1, 1, 0, 1, right? So this is an example of undirected graph. Okay, now if I see this matrix from here, if I cut it from the diagonal, then I get a symmetric matrix, isn't it? If I put a diagonal here, okay, so that upper half of the matrix is same as the lower half of the matrix, right? So this is just an example, again to tell B is connected with BD. For D, it is all the 4 connections. And so the question is it always symmetric? Now, if you see here, it is symmetric. If adjacency matrix will be symmetric for, undirected graphs, right? Is it always symmetric? Yes, it is symmetric for undirected graphs. But if the graphs are directed, we cannot say, right? In this case, it is symmetric. Why? Because the graph is undirected graph. So that's a symmetric matrix. Means you make a transpose of this matrix, you will get the same matrix. Matrix, not matrix, matrix. Yes. Right. So now this is the same example we made it using because we asked a question here, is it always symmetric? So the answer is yes. Okay, I did not write the answer. It is too obvious. It is yes. Answer is yes when the graph is undirected. Now, when you see the directed graph, it is like this, right? So A to B you have. From B, when you say there is nothing. From C, when you say it is only D. From D, when you see it is A and B. And from E, it is only D. Now you see this is not a symmetric matrix, right? So now if I say transpose, this row is not same as this row. This row is not same as this column. It is not a symmetric matrix. It is not. Right? So the answer for that question is, when the graph is undirected, yes, it's a symmetric matrix, adjacency matrix. But if it is a directed graph, then adjacency matrix will not be a symmetric matrix. Simple. These problems can be solved by just taking a simple example and do it. Right? That's about adjacency matrix. So we just want to summarize adjacency list and adjacency matrix. Both have their own advantages and disadvantages. All of you must be knowing that. Right? So let me just show you the picture again to summarize the advantages and disadvantages, or you can say not exactly advantages, disadvantages. You can call them as features. So if I am representing my graph using an adjacency matrix, I will be able to do certain, I will be able to apply certain feature that is easily implementable using adjacency matrix. Okay, so what is that? In general, okay, let me just show it. All of you know this. Okay, so basic use. So first point that is written is, it's not like we are not comparing. The first point that is written is, we are telling you that, where we should use it. Okay, so the first point is telling the usage. Okay, so we should use adjacency list when we have sparse graphs. Okay, you know the meaning of sparse, right? Sparse means when most of the entries are 0. Sparse means it does not exist, hollow, empty. Okay, so when it is sparse graph, for example, web, you are making a connection of web, many of the nodes are not available. Then it is good to do the adjacency list, because in adjacency list you are seeing that from each node what all nodes are connected. So whenever we have a data, okay, we have a graph or we have a requirement, a network wherein we have a sparse graph, we can go for adjacency list. For anything you can go for adjacency list actually. As such, theoretically, you have a data structure, you can as well go adjacency matrix. But what will be the efficient use? So whenever there is a sparse graph, we must use adjacency list. Whenever we have a dense graph, we must use adjacency matrix. Okay, dense graph means there are many connections, so many nodes are connected with other node. So let us use the adjacency matrix, right? That means adjacency matrix means here most of the elements are not 0. So let us use the adjacency matrix. Okay, so what is the use of adjacency matrix now? Okay, the basic use of adjacency matrix is because it's a matrix. Okay, and if you want to see any, if you want to check whether A is connected with B, you just have to access one index, isn't it? If you want to just check whether D is connected with E, you just have to check this particular index. So that is why we call it as it has a constant time lookup to discover if an edge exists. Constant time lookup. If you want to find out whether an edge, because edge will be always between two nodes, right? And if you want to do a lookup, you just have to search for one matrix entry. So that's why it's a constant time lookup to discover if an edge exists. Also, adjacency matrix are simple to implement. Okay, and another good feature about adjacency matrix is if the graph is a non-weighted graph. Non-weighted graph means the graph that we saw, there was no weights on the edge. So it's a Boolean matrix. The entries are only 0 or 1. But if it was a weighted graph, you know what? How do we change adjacency matrix if it's a weighted graph? Now then, rather than saying DA as 1, okay, I will, if it was a weight of 8, I would represent 8 here. Okay, so rather than representing 1 in the weight in the adjacency matrix, we represent the weight in weighted graph, and 0 will still represent that there is no edge. Okay, but rather than saying 1, we will always represent it as the weight. Okay, so that is why we are saying that if the graph is a non-weighted graph, we only require zeros and ones to represent in adjacency matrix. These are the features of adjacency matrix. Now we come to adjacency list. Now if you are going for adjacency matrix, even though there is a connection or not between two vertices, you are allocating that much space in matrix, right? So adjacency list, you will not do that, right? So that's why adjacency lists are good when the graph is sparse. So that then you really able to achieve the feature of adjacency list having space efficient. They are space efficient because suppose A is there are 20 nodes, but A is connected with only 2 nodes, means you will have a place only A with those 2 nodes. So that way we are saving the space. But then it has to be a sparse graph. Okay, so that's why adjacency lists are space efficient. And another problem that does not occur, you say that there is a constant time lookup in adjacency matrix. In adjacency list, what happens? We have to traverse the adjacency list to discover if an edge exists. I want to check from A whether D is connected or not. So first I will go to A, the vertex adjacency list of vertex A. Then I have to keep on searching. From A there is an edge to B. B has an entry, yes. B is connected with B. C has an entry, yes. D has an entry, yes. So if suppose there is no entry, suppose there is a node M which has no entry, but I will come to know only when I have traversed the whole adjacency list, right? Then only I will come to know. So lookup, so that there is no constant lookup in adjacency list, right? That is one disadvantage you can say, or shortcoming you can say. So but now it depends, because they are quite space efficient. So it depends, what problem we are dealing with, right? We want to save memory or we want to save time, right? So all that depends whether we want to use adjacency matrix or we want to use adjacency list. Okay, and there is a best of both words also. Okay, so can we get the best of both? Yes, that is called as a sparse adjacency matrix. That is called as sparse. This is adjacency list, adjacency matrix. The data structure is called as a sparse adjacency matrix. Okay, what is it? So it says that we are not making a matrix basically. We are calling it as a matrix, but we are not making a matrix. But we are using an adjacency list. But rather than using an adjacency list, we are using the feature of adjacency list that corresponding to every, the adjacency list had a feature that corresponding to every node we have an adjacency list. Here we are saying that corresponding to every node, we call it as an adjacency hash table. Okay, so we have a node A. Now node A may be connected with many nodes. Okay, so those nodes we are going to keep in a hash table. It's not a matrix, it's a hash table. Okay, so in this example, when I want to make A, I will say that hash table. I am saying that corresponding to A, I don't have an adjacency list, but I have a adjacency hash table. Adjacency means corresponding to A, whatever is adjacent to A. For that, I have made a hash table of BD. For B, hash table of AD. For C, hash table of D. For D, hash table that is made up of A, B, E, and C. For E, hash table of D. Hash table made up of D. Now, how will it help? Okay, how will it help and where will it help first of all? Okay, so you can understand it like this. Now you want to say that B and D are there. So rather than saying B and D, you are putting where to find, basically what was the problem with adjacency list? Adjacency list, as I told you, the problem was, suppose there are A is connected with 20 nodes. Okay, and I want to search whether a particular node is available, whether a particular edge is there or not, that starts with A. And suppose that edge is not available. Okay, so I'm again repeating the example. Suppose A is connected with 20 nodes. It's a big graph. Okay, and we want to find out whether A is connected with M or not. In adjacency list, what will happen? I will keep on searching all the, and suppose A is not connected with M. So if A is not connected with M, I have to search, I will be searching this list. I'll be searching this list, and searching is an O and time algorithm, right? So I have to search each of the node, and once I reach to the end, I will come to know that M is not available, right? So if something is not available, that lookup time is more. That is the problem with adjacency list. Now, I think that much is enough once I say. Now you just imagine that you are using a hash table. You are not using you are not linearly, you are not using a linked list kind of a structure. You are having a hash table. So you know that if you have stored M, okay, hash table means simple function. You can take mod for an example. You know that if M is in this table, where M will be, right? So you will know that location and you will just hit on that location. So if you find that location, that means it is, you are saving time. You can say almost constant time lookup you can get. Only thing is you need to calculate that calculation time. You need to calculate whatever you want to search, that edge, which node you want to search. Once you know the index of that node, there will be only one place wherein your node will be found. So it will provide you more efficiency in terms of searching time. Hash table. I hope it is clear. So corresponding to every node, we are going to have hash table. But what will be the problem with that? The problem that is associated with hash algorithms, hash table, the same problem we will have it here. So when do we have problems in hash table algorithms? When my table size is really very big, right? You know that, right? Because then what happens? You can, if you can allocate, for two different nodes, if they get the same index, then hashing becomes a problem, right? So if the data size is really large and you want to do hash table, okay, it will be a problem. In that case, what is the solution? The solution is, then rather than using hash table, we better go for adjacency matrix, right? We were not going for adjacency matrix because we wanted to save space. Even if it takes little more time, it's not a constant time. We wanted to become space efficient. That's why we were going for sparse adjacency matrix. But if the size is becoming big, if the data size is becoming big, graph size is becoming big, such that your hash table is not able to perform well, then better we can go for adjacency matrix only. Okay, so you can go through, it is all there in the book, students. Whatever I explained, it is there in the book as well. Okay, so sparse adjacency matrix gives us constant time lookup. I told you, right, how constant time lookup, because I know there will be a fixed index for a particular node. And then definitely they are space efficient because they are not a matrix. They are adjacency list kind of a thing. But again, not good for dense graph. Why? I explained you why. They are not good for dense graph. Why? Because that is the basic property of hashing. If the graph is dense, then it may happen is that B has 20 nodes to be placed in a hash table. right? So for many nodes, there can be the same location. Then you will have to apply the algorithm that, okay, if the location is same, where should I put it, right? There are solutions for doing that. So in that case, it will not make my constant time lookup. So what is the use? Rather than that, we can go for adjacency matrix itself. All right. So I think we will wind up with this, students, for today's class. We'll continue in tomorrow's class with weighted graphs, and yeah, let us see. Okay, let us see tomorrow and day after how much we are able to cover. All right, students. Thank you. Any questions are there? You can ask. Else we will wind it up, students.
Ma'am, can you share the syllabus for mid?
I have not shared. I think I have shared. No. I have already shared, students. So L7 and L8 till L8, lecture 8. Okay. I think I had told for L7 previously. So let us keep it till L8, students, or else let us see. L8. If I am not able to cover L8 completely, okay, let us keep it till L7. Okay, done. We will do it. We will start L8, but let us keep it till L7 graphs. Okay. Fine, students. So I will upload. I will I will post also the syllabus will be till L7 for midterm. All right. Thank you, students. So I will wind up. Thank you, students. So I will upload this L7. I will upload if today or tomorrow. I must upload L7. So that will be midterm syllabus, but we will definitely continue. We will definitely continue with L8, students, because I saw yesterday. I was really upset because your midterm is taking 2 weeks time. I just realized it yesterday only that. For midterm we are spending lot of time, means nobody's fault in that. So the midterm week we will not have classes, right? And after that also it was your schedule is like this, uh, till 14th you have exam. I saw, nah? Till 14th you have exam, right? Some viva, yeah, 13th my viva itself. So 15th only we will get back. So 2 weeks will definitely go away for that. So even though we will finish, if we finish midterm portion on Tuesday, we will continue the class on Wednesday, because we simply cannot spare the class. Okay. Fine, students. Thank you. Thank you.
Thank you, ma'am.
Yeah. Bye.